Hi, my name is Jesse Anderson, and in this video I'm going to talk about some of the issues with Kafka Streams, specifically around its database and around its lack of shuffle sort. To start off with, you should already know how Kafka works. I'm not going to explain how Kafka works. I expect you to know that. Another thing you should know is that creating stateful systems, real-time stateful systems, it's incredibly hard to do. So this is something you should know when you start embarking on a journey, whether it's with Kafka Streams, Kafka Period, or other real-time systems. It's incredibly hard to get stateful systems right. So I really want you to know that. Another thing you should know is that all of the issues that I'm talking about with Kafka Streams also extend into KSQL DB. So let's get started. To start off with, we have our Kafka cluster. So with our Kafka cluster, let's imagine we have Kafka here, and I'm just going to put a big K there for our Kafka system. Now, when we have Kafka Streams appear as regular consumer producers. There's obviously some syntactic sugar behind the scenes that is giving us some Kafka Streams. So here we have a Kafka Streams process, another Kafka Streams process, and another one. So we have these Kafka Streams process. Those could have the same application ID and form a group of machines where the work is going to be distributed based on partitions. Now, one of the main issues with Kafka Streams, if we kind of explode this out, we have our Kafka Streams code, and we have our code that we've written. But there's also a database that's on every single Kafka Streams machine, on every single Kafka Streams process. And this is one of the big issues that I think is not very well explained or not very well known within Kafka Streams. Now, this database is backed by RocksDB. It's basically a RocksDB database that is on every single one of these Kafka Streams machines. Now, here's the issue, is that every single one of the mutations that happens from the code into that database actually goes into its own topic in Kafka. So we mutate here, we mutate. Every single one of those mutations, whether it's changing from 1 to a 2, whether it's changing this or that, every single one of those mutations goes into its own Kafka topic. Here is where we have something that's nice, and that is that we can use Kafka for that durable storage that's fault tolerant, and I'm not arguing about the fault tolerance of Kafka in this video at all. But what we have is we have all of the data from those mutations going into a specific topic in Kafka. Now, here is where things get interesting and difficult, and that is specifically around what happens when we start to have problems. All these distributed system designs are well and good in a steady state, no issues. This all just works just fine. But the biggest defining characteristic of distributed systems is how well they plan for problems. How well do they plan for failures? And with distributed systems, you can't say, once in a blue moon, I'm going to have a failure. We have to spend a significant 95% of our time thinking about what happens in those failures. Because we have an issue now of how do we recreate the state for that RocksDB? And that's what a lot of my initial issues are around. What happens? How do we create that state? As I mentioned, we have all of that state for the database. It was initially stored in Kafka. So what happens here is the state can be replayed back from Kafka and put into that RocksDB. Now that all sounds well and good, but there's some issues there. We won't lose state, but the question is, how long does it take for state to get back? How long does it take for this to happen? Because while this is waiting and all this data is being put in, we can't have this Kafka Streams processing. It's waiting for its entire state to be recreated before it can start working. And that is a big question. Depending on who you ask, I've heard people say that this recreation of state, this step right here, can take 15 minutes, 30 minutes, hours, and that is a big issue. So to kind of help you understand my issues around Kafka Streams, my issues are not around the programming side. The programming side is one thing. My issues are around operational and architectural. That operationally, I am really reticent for there to be an amount of time where this machine can go down and that I have to recreate that database, and that amount of time is unknown. It could be 15 minutes, could be 30 minutes, could be an hour, could be hours. And I have talked to people who've said, yes, it takes hours in the field. Now, why? As I mentioned, we have to recreate this entire state by replaying everything that's happened in Kafka. And that is a big issue. One other issue is how many failures there were. Was there a failure of just one machine? Well, that's a different amount of time. But if we imagine that the entire Kafka Streams cluster goes down, that's a different thing. That means that all of that state has to be recreated by pulling it back from the Kafka cluster. This means that there are different levels and amounts of resources that can be used. And that's that high variability amount of time. This is one of those big issues. So that complete failure, let's say we're in the cloud and entire availability zone goes down that we're in, we'd have to recreate that state. That could be a big issue. The power goes out in our data center. That's a big issue. We could have that entire Kafka Streams process, that group of machines go down and have to recreate that from scratch. And as I mentioned, during that time, this Kafka Streams cluster is down. It is not able to process because that data has to be completely recreated before it can start processing. So one thing that Kafka Streams has done is they've created these things called hot standbys. And this is a Kafka Streams process that doesn't do anything. It's just waiting for a failure to happen. So it just sits there, does nothing, waits for one of these other ones to die, and then it takes over that work. And it can take over that work because it's been replaying and listening to all of the changes that have been happening to this database mutation that go into Kafka. It's been listening to as well and been processing them. Now, here's an issue with that is I don't think that this is well documented. This hot standby isn't a best practice from what I've been seeing and in my interactions. This Kafka Streams process is more like an absolute must. This hot standby is basically expected. You are expected to have this, otherwise you will have that downtime. And I think that really needs to be reflected better in the documentation. One other thing that people have said is that in Kubernetes, we could use Kubernetes, or we can use a hard drive. And by having that same hard drive, we're able to maintain those. If you're familiar with Kubernetes, that's called a stateful set. And by having that stateful set, we won't ever lose a disk. Well, as I've listened to experts, and I don't claim to be 110% expert on Kubernetes, but as I've read their commentary on stateful sets, we are really putting a lot of emphasis and a lot of onus on stateful sets doing something that it wasn't really supposed to be doing. So this is, from what I've read, stateful sets are not this guarantee that we won't lose that data. In a very basic sense, I want you to take out of these failure issues that the failure modes that could happen, although there is some planning for them, that the things that have been put forward aren't the greatest ways. So what is typically the best way to do this? Well, here, as I mentioned, if we were to kind of visualize out this data that we have coming out of our RocksDB mutations, let's imagine we had our topic right here of those RocksDB mutations. Every single one of those mutations is an entry. It's a separate message in here. Okay? And one of the big issues is as we change the same key, let's imagine we had key 1, we have key 1 again, we have key 1. Each time it's been mutated, that's a new entry that's in there, in that topic. Now, if you talk to people who are very pro Kafka streams, they say, well, there's this thing called compaction. And what compaction will do is it will take all of these sorts of issues, all of these sorts of keys, and it will merge them down into the same one. If you're familiar with that on Kafka, that's called topic compaction. And that's what they say is the way that all of this is solved. We simply compact this topic down. Now the issue there is that there isn't a single point in time where everything is 100% compacted. But one thing that other systems have done is what's called checkpointing. And in my opinion, this is the most common way, or perhaps one of the best ways, in order to work with sorts of distributed systems, stateful distributed systems, and failure. So what we have with, once again, Kafka Streams does not have checkpointing, and that's one of my key issues. If we compare it to, for example, Apache Flink, so here we have Flink, what will happen is we would consume Kafka in a very, very similar way, but what will happen is often to, let's say, S3 or HDFS, we are going to write out a checkpoint, and that checkpoint is going to say, here is our entire state as it stands right now, our entire state. So that if our Flink process were to die, what would happen is the Flink process would be able to come back up online, retrieve that checkpoint, and that checkpoint is broken up, and then start from there and start mutating its database from whatever point that checkpoint had started from. Now that stands in contrast to what happens with Kafka, where as we have a Kafka Streams process that comes up, what will have to happen is that Kafka Streams process, that database that's right here, will have to start at the very first message of that Kafka Streams, that database mutation topic, go all the way to the end until it is ready to start. And that is an issue. That is a very distinct issue. So which one is more resilient to failures? Definitely right here with checkpointing. So checkpointing although I mentioned Flink specifically, it's also in Spark, but checkpointing is a very, very difficult distributed systems issue to solve. You don't want to solve this issue in your code. You don't really want to do that. That's part of the reason why we use these frameworks in distributed systems, is that they will solve these really difficult distributed systems problems for us. So what we have here is, you've heard me talk about the difference in time. Well, the difference in time is with Kafka Streams, we have to start all the way here and then go to there. That's that issue of taking 15 minutes, taking an hour, hours, that we could have that downtime. But with Flink and our checkpoints here, we should have a pretty consistent amount of time that our checkpoints are happening, or a pretty consistent amount of time that it would take for us to recover from a failure right here. So we do need to take that into consideration. Personally, if I were to have to choose a better failure mechanism or recover from failure mechanism, it would definitely be Flink's. That's a different story, but Flink can use Kafka as a storage mechanism, as a ingestion mechanism for its pub sub. So one other issue that is here, and is a big contrast between Kafka and Flink, or Spark streaming for that matter, is a lack of what's called a shuffle sort. In Kafka, we have a single key. So as you know, there's a key and there's a value for every single message. And then when we have a partition, we have a grouping based on that key. If we have a key, or we can have groupings there by partitions. So the issue here is with Kafka streams, or just Kafka in general, whenever we change off a consistent key here, and we change this key, Kafka streams has to create a topic in the background. And that topic in the background can actually cause a significant amount of extra work for Kafka behind the scenes. Where if we go from, let's say, a key of username, and we'll just say UN, and we change that to company, what will have to happen is that Kafka Streams will create a brand new topic behind the scenes and start grouping based on company. That could be a big issue, that could be a slight issue. It depends on your data set. I would say one of the more difficult and bigger issues is that it is not well documented that this even happens, that there is a creation of a new topic behind the scenes. For example, with KSQLDB, you actually have to look at the explain plan. And in the explain plan, it will say how many topics it's going to create behind the scenes for you. In Kafka Streams, it's much more opaque. As you create your system behind the scenes and as you code it, you may be creating a new topic behind the scenes by changing that key. So it is very important. So what's the big deal about this? Well, the main issue that happens here is that this entire new topic is actually persisted here in Kafka. And although you may be thinking, well, it's just one, if you get into a difficult enough of a SQL query, let's say using KSQLDB, you could be making 1, 2, 3, sometimes more different of those topics behind the scenes. Now, how does that contrast with, let's say, a Flink? Well, Flink does have a shuffle sort. It does have that built in. So what happens with Flink is that we don't create extra topics behind the scenes in Flink. What we do is on the next iteration of the DAG, so we would have our DAG here, and it might go this way and this way and this way. We're not creating extra topics between here as we go to this. Behind the scenes, Flink is handling the shuffle sort for us. More importantly, Flink is handling the shuffle sort and the deletion of that shuffle sort data. Here with Kafka, that data is actually being not just stored, but it's also being replicated. There are some definite issues with handling this. Now, I personally haven't done the performance testing, but I believe and I'm pretty sure that there is a decent amount of performance testing difference that would happen between this because of how the shuffle sorts are being done behind the scenes. So coming out of this video, there's a few things that I want you to understand. One is that doing stateful systems in real time and distributed systems is really, really difficult. No matter what people may tell you, it is really difficult to get all this done right and to program it correctly. And I would say more importantly, operationally, once it's in production, to make sure that it all works right. The second thing I'd want you to take out of this is the differences in how Kafka Streams works from, for example, a Flink cluster. Finally, the third thing I want you to take out of this is the big difference in how Flink and Kafka Streams handle failures. How are those failures done? How fast can failures be dealt with and recovered from? That is a big difference. With that, I wish you the best of luck as you make your choices on these technologies.